There are several advantages working with commands in EViews. Perhaps the most obvious one is that it is generally quicker to type commands than to go through the menu system. You will see other benefits of using commands in this lecture. The default setting in EViews is to display the command and the capture window as tabs. I want to be able to see them both in this lecture, so I will drag my command window. You can attach it to either side of the main window, but I will leave it right here. Let's drag the capture window and put it here. Learning commands in EViews is not simple since there are so many. In this respect, the capture window is very helpful. Let's create a new work file. I will create a page which is undated, unstructured with 6 observations and name the work file WF1. If you look at the capture window, you see the command that you need to type to create an unstructured work file with 6 observations. Let's try this. In the command window, I type wf create parenthesis wf equal to wf2 and parenthesis u6, and a second work file is created. If you want to repeat this command, simply position the cursor on the line you want to repeat, make changes and press enter. You can now create a third work file quickly by simply changing 2 to 3 and clicking enter. You can also position the cursor after the last command, control clicking the up and down arrow until you get to the command that you want to repeat. When you are working with several work files, one of them will be the active one. You can see which one is active in the lower right corner. WF is WF3. Typing commands in the command window will always apply to the active work file. So let's close all work files except for the first one. The next thing we need to look at is how to create objects in a page in a work file using commands. Using the menu system, you create new objects by right-clicking the work file, selecting New Object, or you can click Object, New Object, which you can do in the main menu as well. When you create a new object, you must specify a type and a name. To create a new object using a command, begin with the type followed by the name. If I want to create a series named S1, I simply type series S1. This will create an empty series. To display a series in a worksheet, we can either double-click it or type s1.sheet. Just to have some numbers to work with, I will fill S1 with random numbers. To do this, in the command window, type S1 equal to R and D. You can combine the declaration series S1 and the initialization S1 equal to R and D in one line. I can type series S2 equal to R and D. The type declaration is mandatory in EViews. You cannot type S3 equal to R and D without receiving an error message. Here are some other ways you can create new series. If I type series S3 equal to 5, I get a series where each element is equal to 5. If I type series S4 is equal to @trend, I get a series going from 0 to 5. You can create line graphs from the command window by typing s1.line. If you want to make a line graph containing several series, you can either create a group or you can type line S1, S2. Scat S1, S2 will quickly create a scatter plot, and XY S1, S2 will create an XY line plot. Before digging deeper into series and things you can do with series, let's introduce a new type, the scalar type. The purpose of objects of this type is to hold a single number. Let's create a scalar named C1. Double-click C1 or type show C1 and you see that the scalar can hold only a single number. You can assign a particular element in a series to a scalar. For example, if I type C1 equal to S1 parenthesis 3 and parenthesis, C1 will hold the third element of S1. There is an alternative way of picking out individual elements from a series. I can type C1 equal to @ELEM parenthesis S1 comma 3 end parenthesis. This notation is useful if you have named observations, such as time series data. For example, here I have another work file with monthly data from 2000 to 2017. If I want to store this value in a scalar, it would be very inconvenient to figure out which observation number 2010 month 1 is. You can then type C1 equal to @ELEM parenthesis S1 and 2010:01 in citation marks. The next thing we need to look at is operators and functions in EViews. You can find a list of all operators and functions in EViews in the Commands and Programming reference. Click Help PDF Docs. Let's begin with operators. Note that the operators may be used in expressions involving series and scalar values, and applied to series, the operation is performed element by element. EViews has the standard operators add, subtract, multiply, divide, and powers. For example, if I want to create a series which is the sum of the first two, then I type series S5 equal to S1 plus S2. You can do the same thing in the menu system by clicking Quick, Generate Series, type S5 equal to S1 plus S2. In this case, there is no need for a declaration since you can only create series in this window. We can mix scalars and series. For example, if I set C1 equal to 4 and create series S6 as C1 plus S1, 4 is added to each element in S1. If you want to make calculations without creating a new object, you can use show. If I want to look at the cube of the values in S1, I can type show S1 caret, which means raised to the power, and then 3. If you then decide to keep the series, just click Name, give it a name, and it will be retained as an object in your work file. Note that the icon is slightly different compared to the other series icons. I will come back to this later in this lecture. The remaining operators are logical operators. Greater than works in the following way. If I do show S1 greater than 0.5, you get a new series containing only zeros and ones, with a 1 when the condition is satisfied. EViews is almost ridiculously strict in interpreting commands. If you mistakenly insert a space before or after an operator, EViews will be confused. Say I do this and EViews is lost. The precedence of evaluation in EViews is what you would expect. For example, multiplication is done before addition. Moving on to mathematical functions, which are divided into groups. The first group contains the basic mathematical functions. The first thing to note is that functions are preceded by the @ sign. For example, if I want to calculate the natural logarithm of all values in series S1, I can type show @log S1. Keep in mind that log is always the natural logarithm in EViews. Log and exp are about the only two functions where you are relieved of typing the @ sign. Typing show log S1 will also work. You can also create a new series as log of S1 by going to Quick, Generate Series, typing for example S2 equal to log of S1. I want to point out one more thing regarding the notation of functions in EViews. Check out the round function. As you can see, there is an n inside square brackets. Square brackets indicate that this is an optional argument and n is to be replaced by an integer. For example, let's type show 100 times S1. All these numbers are now between 0 and 100. Let's then type show @round 100 times S1 and series S1 is rounded. we can use the optional argument to round to the specific number of digits. For example, if I do comma 2, I get 2 decimals, and if I do -1, we have rounding to the nearest integer divisible by 10. I will discuss the time series functions later in the course. The financial functions are not particularly exciting. However, a few things needs to be said about the descriptive statistics. Let's begin by looking at the mean function. If I do show at mean S1, I will actually get a series where each element is the mean of series 1. This is typically not what you are looking for. A better way is to store the sample mean as a scalar. If I type scalar sm equal to at mean S1, I will instead get the scalar containing the sample mean of S1. The result of most of the functions in the descriptive statistics section can be assigned to a scalar, but there are a few exceptions such as ranks. Most of the functions in this section has an optional argument s, an optional sample. If you do not supply a sample, EViews will use the default one of the page, this one. Supplying a sample to the function is useful if you want to do descriptive statistics on part of your sample without setting the sample for all objects on your page. For example, if I do show at sum S1, I will get the sum of all elements, while if I do show at sum parenthesis S1, comma, and I do 1 to 3 in citation marks, I will get the sum of only the first 3 elements. We will get back to samples in more details later, but you can also find the information in the objects reference if you look up sample. Next, we have the cumulative statistics functions. For example, the CumSum works in the following way. Type show at CumSum S1, and you get the cumulative sum of series S1. The first elements are the same. The second element in the cumulative sum is the sum of the first 2 elements in S1, and the third element in the cumulative sum is the sum of the first 3 elements in S1, and so on. The moving statistics functions are all very similar. Let's have a look at moving sum. I'll begin by doing S1 equal to at trend. If I do show at move sum S1, 3, you can see that element 3 is the sum of element 3, 2, and 1. Element 4 in the moving sum is the sum of elements 4, 3, and 2 in S1, and so on. Element 2 in the moving sum is now missing since there is no element 0 in S1. For a more concrete and useful example of moving statistics functions, let's create a new page with 500 observations. I'll do series S1 equal to n R&D, which will create 500 random numbers from the standard normal distribution. I'll do series S2 equal to at CumSum S1 to create the cumulative sum of these random numbers. Here is a line graph of S2. S2 is actually an example of something called a random walk. Let's create S3 as the moving average of S2, looking 5 periods back. A line diagram of S3 shows that it is a smoother version of S2. The number of backward periods determines the smoothness. For example, if I increase this to 10, the line graph is even smoother. Moving on to group functions. Remember, a group is a collection of series. Let's do a simple example. S1 equal to R&D and S2 is equal to R&D creates 2 series with random numbers. I'll create a group containing these 2 series by typing group G1, S1, S2. Double-click G1 or type g1.sheet to see the content of this group. The group functions can be demonstrated using the row-wise sum. If I do show at rsum G1, I get a new series where each element is the sum of the corresponding elements in the series in G. all the other group functions work similarly. The by-group statistics are useful functions if you are working with data where each observation belongs to a certain group. Here, I do not mean a group as an EViews type, but a group in a generic sense. We define a series to keep track of to which group a particular observation belongs. Let's create a new series called InGroup. For example, if the first two observations belong to group 1, the second two belong to group 2, and the final two belong to group 3, I set the following values. Say that series S1 is the income of 6 observations, which I arbitrarily set to the following values. Now, if I do show at sums by, parentheses, my series S1, comma, in group, you see that you get the total income group by group. These two values hold the total income of group 1, these two of group 2, and these two of group 3. Next we have special functions and trigonometric functions. You can use these functions with scalars. For example, you can type show at logit of 0. You can also assign the result to another scalar using, for example, scalar r equal to at logit of 0. You can use these functions with series. As an illustration, let's create a new page with 601 observations. I'll do series x equal to 0.01 times at trend minus 3 to get an x variable that goes from minus 3 to 3 in steps of 0.01. I do series y equal to at logit of x, which will calculate the logit of each of these 601 x values. You can now do xy, x, y to create a graph of the logit function. Alternatively, you can do group g xy followed by g.xy. EViews has all of the common statistical distribution functions. For example, dnorm is the standard normal probability density function. If I do y equal to at dnorm of x followed by xy, x, and y, I'll get a graph displaying the familiar bell curve. cnorm is the cumulative distribution function or the CDF function for the standard normal. For example, if I do scalar p equal to at cnorm minus 1.96, we see that p is approximately 2.5% as expected. Qnorm is the inverse of the cnorm function. If I do scalar z equal to at qnorm 0.025, I will get approximately minus 1.96. EViews uses the same naming conventions for all distributions: D for probability density functions or PDFs, C for cumulative distribution functions or CDFs, and Q for the inverse of the CDFs. You can also simulate random numbers from all of these distributions. If I do series S equal to at R norm, I will get 601 random numbers from the standard normal distribution. If I then do hist S, I'll get a histogram mimicking the normal PDF. I'm skipping the string, date, and indicator functions for now, even though the inList function is quite useful. The work file and informational functions are fairly easy to understand. For example, we see that this function returns a string containing the EViews version string. To get the version string, I can type string str equal to at verstr. Most of these functions are useful only if you do programming. I will get back to this later, but for now, let's look at a simple demonstration. First, programs are not supported in EViews student version. Here I'm using the standard edition. I can then do File, New Program. A program is simply a sequence of EView commands that will be executed consecutively. For example, here is a short program which creates a work file with 100 observations. It simulates random numbers from the standard normal distribution and displays a line graph of these random numbers. I save it and then I run the program. Click OK and EViews creates the work file, the series, and displays the graph. The final thing I want to talk about is auto-updating series. If I do S1 equal to @trend followed by S2 equal to 2 times S1, S1 and S2 will be disconnected. Changes made to S1 will not propagate to S2. There are cases when we want series to be connected, and we can do this with a formula. If I do FRML S2 equal to 2 times S2, S2 will be auto-updated. Any changes made in S1 will be reflected in S2. Note that the icon for a formula series is slightly different. It's a line graph with a tiny equal sign. You can remove the connection and freeze S2 by typing S2 equal to @clear. Well, that's it for this introduction to commands in EViews.